Diagonalization is the standard way to simplify a matrix, but it doesn't always work. When a matrix lacks enough independent eigenvectors to form a basis, it's considered defective. To simplify these matrices, we use a broader framework, the Jordan canonical form. Standard diagonalization requires a complete set of linearly independent eigenvectors. If we don't have enough, we can't build a diagonal matrix. We need a way to fill those gaps using a more general set of vectors. This approach relies on a structure called a Jordan block. Inside this block, a single eigenvalue, lambda, repeats along the main diagonal. When we lack independent eigenvectors, we use generalized eigenvectors to fill the remaining columns. In the matrix, one sit immediately above the diagonal. These act as links, chaining the columns together into a single cohesive unit. If we zoom out to the full matrix, J, we see it's a block diagonal structure. The entire matrix is built from these individual Jordan blocks, with zeros filling every other entry. This structure provides a consistent way to represent any linear operator, ensuring that even matrices that can't be diagonalized can still be reduced to a structured block diagonal form. We find the columns for these blocks by iteratively applying A minus lambda I until we reach the zero vector. The power, k, represents how many vectors we can chain together for a specific eigenvalue. The dimensions of these chains follow three specific rules. First, the exponent of the characteristic polynomial, the algebraic multiplicity, tells us the total size of the space. This is the total number of times the eigenvalue appears on the main diagonal. Rule 2 connects to the minimal polynomial. Its exponent is the length of the longest possible chain of vectors. This defines the size of the largest single Jordan block for that eigenvalue. Finally, Rule 3. Every independent chain needs its own starting eigenvector. This means the geometric multiplicity, the number of true eigenvectors, dictates the total number of separate blocks. These three rules allow us to translate abstract algebraic multiplicities into a concrete geometric arrangement. Let's apply this to a 2x2 matrix with a characteristic polynomial of x minus c squared. We have two diagonal slots to fill with the value c. If the minimal polynomial is just x minus c, our second rule says the largest block size is 1. This forces the matrix into a standard diagonal form. But if the minimal polynomial is x minus c squared, the largest block must be 2x2. A 1 on the superdiagonal connects them, forming a single Jordan block. In a 3x3 case, like x minus 2 squared times x plus 1, the eigenvalue -1 has a multiplicity of 1. It occupies its own 1x1 block. The remaining 2x2 space belongs to the eigenvalue 2. If its minimal polynomial exponent is 2, it forms one large block. If the exponent is 1, it splits into two separate blocks. Let's try a 4x4 matrix. The characteristic polynomial is x minus 2 to the fourth, and the minimal polynomial is x minus 2 squared. Based on the rules, pause here and determine the possible block configurations. While small matrices often have only one possible structure, larger dimensions allow for multiple configurations that can share the same characteristic and minimal polynomials. Returning to the 4x4, the characteristic polynomial confirms we have 4 diagonal spaces, and the minimal polynomial tells us the largest chain, and thus the largest block, is 2x2. We could fill the space with 2 of these 2x2 blocks. This satisfies every rule we've established so far. But we could also use one 2x2 block and two smaller 1x1 blocks. This still respects the rule that the largest block is size 2. To decide between them, we need the geometric multiplicity, the number of blocks. We find this by calculating the nullity of A minus 2i. If the nullity is 2, we have 2 eigenvectors and 2 blocks. If it's 3, we have 3 blocks. The number of independent eigenvectors determines the final structural layout. The Jordan form provides a structural layout that accounts for missing eigenvectors, turning abstract algebraic properties into a concrete grid of blocks. If this breakdown helped you navigate linear operators, subscribe for more technical insights.